Okay, my name is Evans. For those who have not been able to interact with me, I'm currently a senior software developer at eHealth. I started out last year on 1st of August, so I currently have 1 year at eHealth, and I've joined the team here 2 months ago. So today I'm going to be presenting compilers and Node.js. So the title of the topic will be, as you can see, from compilers to Node.js. And we will be looking into, first of all, compilers, and then V8, which is a JavaScript engine for mostly Node.js and Google Chrome. And then we will be looking into Node.js internal, some of the things that we can find there. So without further ado, so let's get started. So currently, today we're going to be talking first about compilers, V8 as a JavaScript compiler, and then we will look into V8 and Node.js environment, which is the JavaScript engine V8 in the context of Node.js, and then finally we're going to close with Node.js internal. So I've managed to have some couple of demo and source code within it. So hopefully we can have time to go over everything. So what are compilers? Compilers are mostly a program that translates one source code to the other. Compilers are a software program that will help you read from some source code file of kind of specific program from one language, understand it, and then translate into another language. It can be another source file, it can be compiled into a machine code. At least it will always compile to another source language for other purposes. So most of the time, the source language is usually the language we are compiling, and the language that is outputted will be called the target language. As part of the compilation process, the compiler may need to report warnings, errors, and then we also most of the time need to optimize the generated code, because compilation is not just about translating from language to the other. We also need to consider what are the things we can improve while generating the code. It's really, really bad if you have a compiler that compiles from one source language and generates some target language, and when you run it, it starts running slow, and this is really, really bad. And I think this also affected the Java programming language right from the beginning, but lot of things have improved in the Java compiler, so nowadays people are really happy with it. So the bigger picture is, just as you can see from the presentation at the bottom, is from one source program, you run it through the compiler, and the output you will get a targeted program. So compilers are a bit of black box, but they are not really complicated, especially if you break them down into multiple phases. Compilers have generally 4 main phases, but in some compilers you will find more than those 4. It depends on how you want to architecture the compiler, basically. The first step will be feeding the source program into your compiler, but once your source program is fed into the compiler, you will see that the first step is called lexical analysis. The lexical analysis will do his job and then pass the information to syntax analysis, and then the next step will be intermediate code generation, and the last step most of the time is final code generation. But as I said, it's not always those 4 steps. Along the way, you will have optimization that can come over, and sometimes at the 3rd step, which is intermediate code generation, you may have multiple repetition of code generation. And most of the time, these kind of compilers are called multiple pass compilers. They don't just run once inside your source code. Sometimes for the purpose of optimizing the code, they should be able to pass multiple times through your source code, analyze it again, and sometimes even reshape it. So I would like to go back from the first step and then start explaining a bit what does this first step and the second step and others are. Lexical Analyzer is also called scanner sometime, or even tokenizer for simplicity. Sometimes some people will call tokenizer, some people will call it scanner. Basically what the scanner or lexical analysis will do, it will help you break down all the source code you fed into small chunks. So if, like, let's say with the lexical analyzer we have here, this lexical analyzer will take the source code, it will break it down into small chunks, which are usually called token. As part of this scanning process, if you have a source code, just like in my slide here, if x equal y, then z equal 1, or else z equal 2, when you run through the scanner, the first step, you will end up having tokens such as if, and then the next token will be x, the next token will be equal, because according to the specification of the language we are talking about here, most programming language nowadays will take this as the equality operator, and then you have y, then, and so on. So most of the time, inside the compiler, a token will be identified by a type, a position, and a value. The value, for instance, for the last one is a semicolon, and the type can be a statement separator. It all depends on the programming language you are dealing with. Like if we are dealing with JavaScript, this is like a statement separator, which in the context of JavaScript is not mandatory, but in other languages such as C#, C++, this is mandatory. So it all depends. And most programming language, before even you go to the compiler, you need to specify a way of structuring the language. These specifications are usually called grammars. So, and grammars are actually rules that apply to the language that helps you control the sentences of the language in order to be able to parse it, in order to manipulate it, and so on. Nowadays, programming language are mostly specified in a syntactic rule called Backus norm form. I couldn't go over all this theory behind it, but what it basically means is just like if we take like an English language, what are the rules that we can have in order to make a good sentence? That's all it's about. So basically, from those rules called Backus norm form, you will be able to basically check if a sentence or a word is actually correct or not. And the compilers world have so much evolved that nowadays we have tools that can help you even generate lexical analyzers and parsers. Just because we can read those grammars, understand them, and generate compilers from them. But right now, coming back to, that was the theory part, coming back to our example, the type will, for instance, will be a statement separator, and the position will help you report errors. Like if there is an error at line 1 and colon 60, I will be able, from the position of this token, to say to the programmer, hey, there is a missing semicolon or whatever at this position. So that's why this information, collecting this information at the scanning level is really, really important. Then you have the next step. I hope you guys always keep this bigger picture in mind. So then you have the next step, which is syntax analyzer. The syntax analyzer is also called parsing. And a syntax analyzer, also known as parsing, this process is about understanding the structure of your program. Like let's say, coming back to the English word, if the verb, where is the position of the verb, the adverb, the article, and so on. So this is what's all about the syntax analyzer. It should help us understand what is actually written from the programming language perspective. So coming back to our source code, the syntax analyzer end up giving us a tree. This is mostly because of the way programming language are structured. A tree is the best data structure that we can use to represent them. So you end up having this kind of tree, whereas if x equal y, which is a relation, and then ends up with being a predicate. And if we come over the then statement, we will have an assignment called z equal 1. And if we come over to the else branch, we will have an assignment also called z equal 2. So basically, at the root node, you will have if else statement. And then from there, you have 3 children, which are predicate, then statement, and else statement. In some programming language, the else statement is not required. So if it is not present, you won't have that branch there, and so on. So most of the time, that's what the syntax analyzer will output at the end of the day, which is this tree is most of the time called parse tree. So once you have this syntax analyzer outputting the parse tree, you have an intermediate representation. But while the parsing is done, I'm coming back again to this bigger picture, because you will have something on the side, on the left side, called symbol table. What is a symbol table? A symbol table is like a data structure or dictionary that helps the compiler understand what is going on. When we are parsing, for instance, this little program, we have x, which is an identifier, y, which is an identifier. Sometimes the programming language, the compiler needs to know whether x has been declared or not. So in order to be able to track all those stuff, the symbol table is the data structure that can hold all this information. Has x been declared, and what is its value? What is the data type? If we are running inside a programming language which is statically typed. So then you have semantic analysis. At the semantic analysis phase, now we try to understand and validate the meaning of the program. And as you can see from the bigger picture, the semantic analysis here will be embedded inside, will be coupled with intermediate code generation. So the semantic analysis will help us validate function call, like number of argument that is being passed, and also type checking. I mean, if we are in a language that is statically typed, such as C++. So at this phase, we try to catch all errors early and then report and stop the compilation process. This process will produce a more compact version of the syntax tree. So basically, this tree, the parse tree that was given to the semantic analyzer, after semantic analysis, will have a more compact tree that is called abstract syntax tree. And this abstract syntax tree basically is the syntax, the parse tree that we had, but we got rid of all the junks that was in there. Some of the information that was not useful, we get rid of them. So from this slide, you will have an example of 2 trees. On the right side, you have a parse tree, which is outputted from the syntax analyzer, and on the left side, you have an abstract syntax tree. The operation we are trying to run here is 2 multiplied by 7 plus 3. And if we run this inside our compilers, you have, most of the time, the parse tree is directly generated from the grammar, the Bacchus-Nord form I referred to earlier. So you usually have all of this information hiding in, which will be the overall 2 multiplied by 7 plus 3 will be an expression. And an expression that we have, the overall expression we have is a term plus a term, which is because in terms of arithmetic expression, we will have multiplication which has higher precedence than addition. So multiplication will bind more than the addition. So that's why the leaf node here will be a factor multiplied by a factor, which is 2 multiplied by 7. And then which will be a single term on its own. Then you have the term plus the other term, which is down from a factor. But when we see here, there are a lot of nodes, and basically what we try to extract is the factor, all those nodes that refer to factors, term, we can eliminate them. And when we eliminate them, we found out that our abstract syntax tree just become, okay, this is a plus expression at the top of the tree, and then we have on the left side a multiplication expression and a tree which is an integer literal at the right. Then on this multiplication expression node, we have integer 2 and integer 7, which are the nodes. So basically the end operation will be, if we were about to interpret this one inside directly how compiler, interpreters, we'll just say, okay, we are going to evaluate 2, which is evaluate itself to 2, multiply by 7, then we obtain 14, and then adding 14 to 3, we obtain just 17. So that's basically the evaluation of how abstract syntax tree, and this is most of the time what goes on about the intermediate representation that we have here. And it is only from this abstract syntax tree we will be able to optimize. We cannot optimize based on the parse tree because the parse tree has a lot of information. We can, of course, but it will be really slow. So most of the time we prefer to analyze it first, extract some of the junk, and then have an optimized version of the tree before processing it. So I would like to stop a bit from what we have been going through and see if anyone has a question. If not, I can just keep on going.
Just to say, maybe on the discourse will be open to precedence.
Okay. Jasper is talking about operator precedence. Yes. Operator precedence is a topic which is based on the arithmetic side. I thought of not including here because that was going to the theory. But then most of the programming language, as in best practice, you wouldn't write an expression like this, 2 multiplied by 7. You will prefer, this is an implicit expression. You will rather prefer to write explicit expression using parentheses. This is what is really recommended. But then if we go inside operator precedence, you will know that plus and minus have the same precedence level, and multiplication and division have the same priority, but then plus binds more, multiplication and division binds more than addition and subtractions. So these are the basic idea for the arithmetic. So if you have an operation that has no parentheses like this, which is not grouped, you will assume that first of all you need to do multiplication and division together before trying to do addition and subtraction. But how about if we have plus and minus in the same line? The rule is if you have two arithmetic operations that have the same precedence level, you will evaluate the expression going from left to right. So if, let's say, I replace this multiplication by minus, you don't have to worry about, because minus and plus have the same priority. You just do 2 minus 7, you calculate that, which is minus 5 plus 3, which will be evaluated to minus 2. So that's just the way it goes.
So we say, why is the tree uniformities? Why this kind of tree?
Oh, why is the tree uniform? It is. Just like I'm again saying, the first operation to evaluate here is the multiplication, because the multiplication binds more than the addition. And one thing you need to know is most of the parsers, when we are trying to evaluate this kind of tree, we don't traverse the tree we always traverse the tree into using in-order traversal or post-order traversal. Never evaluate this tree using pre-order traversal, because if you evaluate it using pre-order traversal, then you're not gonna find the right answer. So that's why That's why we end up having this tree like this, because you always have to go, if you go using in order traversal, you will hit the node 2, then you will multiply it by 7 before coming back to the plus. But if you do a post order traversal, then you're not going to find the right answer. You will do the other way around. So it depends on you how you want to shape your. I could flip this tree the other way around, like putting 3 on the other side, but then the way you need to traverse the tree still needs to be always consistent. Otherwise, you're not going to evaluate it correctly. And most of the time in standard way, we rather prefer to put all operation that needs to happen first at the leaf node, because this is we will be doing in order or post-order traversal, not pre-order traversal. Okay. So Jasper, I think you are the one raising the question. Am I clear with it?
Yeah, all good. Thanks, Emmett.
Okay. So just to resume, it depends on the way you are willing to traverse the tree. You could definitely create your compiler and put the tree in the other way around, but then you will need to change your strategy of traversing the tree. So coming to the other phase is optimization. Optimization is most of the time the last step we need to do before starting output spitting source code. And most compilers don't do one single optimization. They will do so many optimization and many passes to the tree, traverse it multiple times until all the rules have been applied or none of the rules is able to optimize the tree. So basically, optimization is about automatically rewriting the program so that the end result will run faster. It uses less memory and most generally conserves some resources. That's all about optimization. So I'm going to walk through some of the optimization rules we usually apply. This is not like an exhaustive list, but it is just about giving you a general idea. So one of the easiest optimization rule we can apply is called compile time evaluation. Compile time evaluation is really simple. If you look at tools like SAS or LESS, what about compiling CSS code into SAS code into raw CSS? You will find this first instruction in the diagram down at the bottom, which is A equal 2.718 divided by 2. Most of the time you will find this kind of expression in SAS, which is about maybe you are building a grid system. SAS will compile this and output the exact result of this division. Because as a software developer, you don't want to be dealing with a lot of floating point precision. You want the end language to deal with that. But then inside a programming language, doing a division is really expensive for those microprocessors. So instead of waiting, like embedding this instruction, asking the CPU to execute this instruction, what you will do during the compilation is you will evaluate this expression from the representation of integer or floating point, do the division at compile time, and then just say A equal 1.3.5.4. I omitted some of the precision, of course, but you get the idea. This is just about evaluating the end result and then putting the end result there. So this is basically a simple optimization, but that can give you a lot in terms of performance in the perspective of your end result program. It might be your exe or your interpreter. So, and then the next level of optimization could be dead code elimination. Nowadays, compilers are really smart. As soon as you write a dead code, it will warn you, hey, there is, like if you do an early returns that doesn't make any sense, it will just tell you, hey, there seems to be a dead code. This space of the code will never be reached. So you can delete it, but in compiled programs such as C++ or Java, even if you leave it, you compile it, it doesn't mean it's going to be spit it out inside your end result program. Compilers are smart enough to get rid of it on themselves because they know that it's never going to run. So, and if it stays there, then it's just going to increase the size of your end result program, and which is about consuming memory. So no one wants that. So that's usually basically what's happened. Then one of the optimization rule that we also apply is called frequency and strength reduction. What about frequency and strength reduction? Strength reduction is about operation that cost a lot. In CPU, if you talk about division and multiplication, these are operations that are CPU intensive. So most of the time we want to reduce requiring to call those kind of operation. If we are able to avoid the call to this kind of operation, we do so through the compilers. If sometimes we cannot, so we just leave it like that because we have to. But in the programming perspective, we all know from an experience that division is most of the time a right shift, and multiplication is most of the time a binary left shift. So if you are trying to divide, let's say you say C equal D divided by 2, any division that's any number that is divided by a multiple or 2 exponent x will mean I'm dealing with a right shift, a right binary shift. So instead of going through, because this simple operation, as you can see, C equal D divided by 2, this means in a CPU perspective, this means, okay, I have C, I need to first push C in a register, then I need to push the value D inside the register, then I need to put integer 2 inside a register. Then I need to call the operation div from those registers. The operation div knows which registers to use in order to do the calculation. Then when the operation div will do the calculation, it needs to pop back the result inside C where C is located. And then this involves like 5 CPU instructions just inside assembly language. So in order to avoid those 5 instructions, we detect that, okay, this is a division by a multiple of 2, which is 2 exponent 1. Then what I just do is, okay, I'm going to say C equal D binary shift on the right, 1. So if I shift the binary representation of D to the right on one step, I just get the result of the division by 2. So this simple operation is optimized using binary right shift. And then down here you have an example. This is what is called strength reduction. Down here you have an example of frequency reduction when you have A equal B multiplied by 4. Sorry, I was trying to say the previous one is called frequency reduction, and the next one should be called strength reduction. Because you have here A equal B multiplied by 4, we will detect that, hey, multiplication is really expensive than doing addition. So what I can do is, I can just take B multiplied by 4 is, I can say it's B plus B plus B plus B. So I end up having an operation which is less expensive. Also, I will have multiple cycles, but it depends on the assumption you have and the information you have from your runtime, from the information you have in the runtime. So I end up having an addition which is less expensive, but then I detect that, hey, this is using a lot of plus. So instead of this, I only detect that 4 is again a multiplication by a multiple of 2. So if I have a multiple of 2, then that means I can just do a binary shift on the left. So I end up having, okay, A equal B, binary shift to left by 2. Then I end up having the result. So these are the basic operations we can apply to the end source code in order to the abstract syntax tree in order to have a much more optimized source code. So before I go to the demo, do you guys have questions about the previous step from the optimization perspective? All right, I guess we don't have. Okay, I guess we don't have questions. So I'm going to try to go through really what I call ultra tiny compilers. I brought the idea from this link. You will be able to have it. This is like an implementation of a really tiny compiler in JavaScript, and you will see that the component we use here in my implementation is even smaller than the super tiny compiler, so I decided to call it ultra tiny compiler. We only have three steps here, which is the lexical analysis, the parsing, and the code generator. I don't apply any optimization. So I think I'm going to first run a demo of it, and then we are going to go through the source code and explain in terms of implementation how all these things work down. So basically, I will try to have a to create a small programming language, just like if you have been able to touch a programming language, a functional programming language called Lisp. This is basically how Lisp is syntactically structured. If you are planning to call a function, you open a parenthesis, you write the function name, and then the following parameters that comes, you just write them and you close the parenthesis. So basically, I have a small language that will support print, add, subtraction, division, and multiplication. And these are like, the first line is one instruction that should print 12. The second line is an instruction that should add 2 and 2 together. This one should subtract 4 minus 2, and then the other one should add 2 plus the result of subtraction 2 minus 4. So you have a small program here that should evaluate this. And what I'm trying to do here is not interpret it and show the result to the console or whatever, but what we are going to try to do within this tiny compiler is compile this to a runnable JavaScript program. So just as I said, I'm going to first run a demo of it. So this program that I've written here, program is called, I'm going to pass it to the lexical analysis, and I'm going to obtain a list of tokens. And after the list of tokens, I will be able to parse the tokens and obtain an abstract syntax tree. And then I will end up passing that abstract syntax tree to the code generator, and I will end up having a JavaScript code here. And that's JavaScript code. I'm just going to output it from inside my console. So when I run it, this is basically what I end up having. And I end up having this. This is like a self-calling function where I pass some function that are already defined, which is print. I define print here. I define add, subtraction, and division here. And basically, all the program I wrote is just over here. All the other part that are not highlighted are just like decorator from my compiler. This decorator will help me create an execution environment for my compiled languages. So as you can see, I'm passing here an argument which is add, sub, multiplication, division, and print. And also remember this because we will be seeing this example when we'll be looking at NodeJS internal. We will have a look at something that is really similar to this. So basically, I'm just trying to call this function, this anonymous function I created here, by passing the addition, as you can see here, and the subtraction here, the multiplication and the division here, and finally the print as just like console.log. So I will just leave it. I'm not going to. Okay, let's just copy it and run it inside JavaScript's runtime and see what we can get from it. Oh yeah, I think I forgot to copy some part of my source code, which should be, yeah. So basically, as you can see, this will output 12, print Alex, and then print the result of the last operation that you can see here, which is add 12 subtraction 73, and so on. So just going to close this one. Yes, and then come back. Yeah. So basically, I forgot this last part of my source code. Anyway, but now let's say we want to go over back the source code. We're gonna debug as we long show you the. But then, if we are willing, this is the lexical analyzer, which is called the scanner, and this is the code generation part. But one thing that the lexical analyzer needs to output is tokens. So tokens, I just created a small class here saying the type and the value. As you can see, I'm not getting the position because I really wanted to keep the compiler really simple. So there is no error checking here. So let's say, for instance, there is kind of error, the compiler will just crash out and stop. Because these are things that will make the source code a bit heavier. I do not want. I just wanted to give you the bigger picture. So inside the Lexer, we will declare an array of tokens. If you have an array of tokens, then we have the position, which is initialized to 0. The position is actually a cursor that will go through all our source code, character by character, understand what is this character and what should I do with the character. So the current character we should be looking at will be a variable called character, and we initialize it to null, which is known in Python. By the way, I'm not a Python expert. I'm just trying to learn Python, so I decided to implement this in Python just for the sake of this demo. So we have some constant I'm declaring here for regular expression matching, but normally regex are mostly expensive. So you should try to avoid these kind of stuff inside a real compiler. So what we do is we will go through all the source code trying to know why the position is less than the input size. The input is just like the source code that we are giving to the Lexer. And we get the current character we are looking at from the input position. We check. If it is a white space, as you can see, white space here is anything that is tab, space, and so on. If it is white space, we don't care about it. We just skip this character by using position equal plus 1. Then then we continue. We skip that one, and then we get the next character. So if the next character is an open parenthesis, we'll create a token. The name of that token will be, the token type will be L parent, which I call left parent, and the value that we are passing it will be the current character we are looking at, which will be obviously the open parenthesis. And of course, because we have just got that character, we need now to consume it. We consume it by usually incrementing the position of the cursor and then going to the next step of the loop. If we we detect that the current character being passed in is a figure, which is whether a figure from 0 to 9, then we just detect that, okay, we will be dealing with a number. Then we create a variable here called number that will be an accumulator to store the characters of the number. Because most of the time you will end up having a number, not just 1 or 2, but something like this. And also this tiny compiler doesn't handle something like this, or even further, 1 to exponent 23 doesn't handle this kind of number, so we only handle here integer values. So basically, as in the same line, to keep things really, really simple. And once we detect that, we enter inside another loop. We check for inside this loop if whether the next character is always a figure, and if it is a figure, we concatenate that to the current number accumulator we are having, and then increment the position. And then when we increment the position, we also look at the next character. And by the way, this kind of look is usually called in compiler construction as pick. Basically, we pick at the next character that is coming. We don't consume it. And once you increment the position, this is called consuming a character. This is called picking at a character to see what this character is all about, but without consuming it. Then once we know what to do with that character, we need to consume it to skip that character. And skipping it is called consuming. Then we do this until we find that, hey, this character is no more a figure. And if it is no more a figure, then this while loop will be closed. Then we all have the numbers that we wanted to get. We create a token, which is of type number, and then we append that to the current tokens array we have. And then we continue to the next character. If the next character that is coming is double quote, then this just means we are dealing with a string representation. A string representation which is in double quote. Then almost in the same idea, we also create a variable called str which will hold the string we are dealing with. But this time, because the first character was a double quote, we don't want to take into account that double quote as part of the string literal we are dealing with. So we skipped that first, this first single quote, and then we pick at the next character. We start checking. Unless the next character is different from double quote, we'll be consuming every character that are coming. And when we hit the closing double quote, then we end the character, the string literal, and we just return back at the end the string token that we have with the string we have just built. And by the way, I'm just trying to say we are not doing any error checking. So this is really important because we are not doing any error checking. Let's say somebody wrote a string like this without the end. Our compiler will just be in a bad state because it will never end. It will just find out that, hey, this string is going far away, so it will just crash up once it hits the end of the input. So if you are trying to improve this source code, it's better to have error handling inside. So basically, that's all about having scanning a string literal. And then we have identifiers. Identifiers are like variable name or function name or library function name that we want to call. It's again the same thing. If we match an identifier, which is usually an alphanumeric, an alphabetical string, if we hit that kind of character, then what we just do is create the identifier and accumulate the name of the identifier inside. Then we, again in the same line, we construct the identifier, create a token of that identifier, and then append that to the token list. If we exhaust all these cases without recognizing the type of character we are dealing with, then now we can say that unknown character and we raise an exception. And this is mostly like raising a compile time error that is, okay, we cannot really compile this, there is error. So if you are trying to build a compiler, this is the worst way of dealing with errors. You need to output something that is meaningful to the user. At least the position where this character was found should be displayed to the user. Hey, at this position and at this line and at column this, we could not match this character. So that's all about, and then we return the token list. So that's all about what is lexical analysis. So let's say, for instance, I go into debug console, and then I try to debug this source code. Yeah, I will just hit here. And then let's say, for instance, I have already my program inside the environment, the debug environment. So let's say I want to get the tokens. So I will just say TKS equal Lexer. Then I want to pass in the input we want. And then let's say I want to output TKS so that you guys can see the actual values that we have. So you end up having 17 tokens from our input program. And the first token, as you can see, is a left parent, and the value was this, just like this one. The next token is an identifier with a print. This is like the representation I gave to what we had. So basically, you end up having all of these tokens inside. So that's what we can say about the lexical analysis. Then we have the next step, which takes the tokens and then output the abstract syntax tree. And the same line goes for the parser. The same way you interpret a lexer, you should be able to interpret a token, the parser, the same way. So you will be having an array of tokens. You loop through all of them, and then you start constructing your abstract syntax tree. So this is how it goes. I have a kind of closure here that is work, but then an abstract syntax tree, what I'm trying to build is a program. If you look into our source code here, this is basically, and this notation will be how a program is called from our grammar perspective. The whole source program will be a program. And then within a program, you have a statement. For each line, you will have instruction statement, instruction statement. Then inside an instruction statement, this is like a call to a function. And again, another call, again, another call. So that's all there is to our programs. So then inside our abstract syntax tree, because it is a tree, so I created a class which is called node, and then the type, and then the value. And you will notice that, if I can just expand this, the third I just inherited from token, but I added another parameter which are called children. Because we need these children, because from the node perspective, we will have children, whether it is intermediate children or leaf children. So basically, what I will do now is the root node of our abstract syntax tree is the program. For now, the value is nothing. And then I will look through all the tokens we have had. I will append the abstract syntax tree children. I will append what is inside work. So I will be able to work the token array, detect what is the kind of expression we are dealing with, and then append that to the children of our program root node. So I will declare the position here at 0, and then enter getting the token. Just the same way as we were getting the character, we will be getting the token here. And once we get the tokens at this level, we also need to check if the token type is a number. If the token type is a number, we consume it, we create a node of type number literal, and the value will be actually the number we are passing it, which is the token dot value. The same way, if it is a string, we always know that the token value will be the string we pass in, so we create a string literal, and so on. If it is a left parent, this is where the things come in. If it is a left parent, we know that we are entering a function call. So we call that a call expression. We create a call expression node. We hold on to here. But inside the call expression node, from this perspective, you know that this is like a recursive call. Because inside this call expression node, you have another call expression node. So in order to support the recursive expression, we need to go into a while and then say that until we hit a right parenthesis, which is the end of the call expression, we need to create, to append inside the call expression children, we need to append another walk while maintaining the current position. And because this walk is a closure, it always have access to the global position we have here, which is why I wrote this one over here. So basically, by calling this recursively, we will be able to build call expression and support expression that are inside expression. At the end, we just return the call expression. And then, so I think I should uncomment this, sorry. If, again, the token doesn't match anything, we just say, okay, unknown token, just as we did for the characters. So we did say unknown token. So let's say I have this token that was, I still believe that I have my, do I? Yes, we do. We have it, we still have the process running. So let's say I have now my token. I want to obtain an AST. I will just say AST equal parser and then pass in TKS. Then I will output AST. And once you have AST, this is like the long string representation. But if I expand it to see what are the stuff that are inside, you will immediately notice that there is nothing on the root node. But inside the children, you have a call expression, which is actually our first part of the program over here, call expression 12. And then you have a second call expression, which is bind to a string literal, and then you have another call expression which inside has a call expression. So let's say we expand this one, you will notice that inside you have another call expression which is add, and the children is number literal, another call expression that I can expand and further. So you basically end up having this kind of tree that you can later on evaluate or generate the source code. So as part of the interpretation, I did not write an interpreter, but from the code generation, as you will see, you can easily generate, you can easily fill in this function to interpret directly from within inside Python. So I just leave it as an exercise for those people who are going to have time to have a look at. And then if you happen to fill in the interpreter, you will just need to uncomment this, and then you have a READPEL interpreter, which is read, evaluate, print, loop interpreter that will be able to read from the command line your source input program and then just run it directly. So the last step is the code generation. The code generation is really easy. So this function, as I was saying, like when we outputted our end result, this is where the template is from. So I create an anonymous function in JavaScript passing these, accepting these parameters, and these are like libraries function. I mean, basic function that are available inside our programming language that you can use from our source code. That's why inside our programming language you can use add, sub, multiplication, division, and print. So the end result, I will replace code with whatever the source code we have compiled here, and this is just like the template of the source code we will output. So I just run through all the children and then call generator to node while appending a semicolon, because JavaScript needs semicolon. Nowadays it's not mandatory, but I'm planning to output in the same line, so I will just say, okay, output with semicolon and then template replace code with the actual generated code we have here. So if you have having this, then what is about the generator code doing? The generator will notice if the abstract syntax tree, the node that is coming, the type is string literal. This is all what we do. We just replace the abstract syntax tree value, the node, and then we put inside double quote. We return, and then if the type is number literal, we just return like 12, we just return it. Again, if we have a type of call expression, then this is where we go inside the children of that call expression, and then keep calling recursively, generate while putting semicolon, which are the actual parameter of the functions that are coming. But because of the last one, we need to remove the last semicolon that we are putting. And then at the end, we just format the value of the call expression, which will be add. We open the parentheses and we close the parentheses. Inside, we put all the argument we have got. So we return that result, and that's make it a call expression, a final call expression. So if I can see what are the value we currently have, local value, we have AST, we have cout. So I believe that we have AST. Then if we say code equal generator by passing the AST, and then we spit out the code, yes, you will end up having this source code that is perfectly a JavaScript source code that is able to run somewhere. So basically, this is how generally a compiler will look like in a real world. There are a lot of type checking I've skipped to make it simpler to understand, but most compilers are based on these simple building blocks. So I believe that if anyone has a question at this demo level, this is the right time before we can proceed. Can you hear me?
Yeah. Just.
Okay.
Yes, we can hear you, Evans.
Okay. It just seems quiet, so I'm just checking if I'm not talking to myself. All right, so let's move back.
Yeah, I mean, I can hear you. I don't know about the Shalom guys.
Yes, okay, thank you. So let's go back. So after compilers, we now go into the world of V8. So V8 is a JavaScript engine, and it's basically a compiler, and that's why we needed to talk about compilers before talking about V8, if you really need to understand what V8 is all about. V8 is the Google JavaScript engine, which is open source. It is purely written in C++. It compiles JavaScript into machine code using a technique that is called just-in-time compilation, which is compiling source code on the fly. It is not like ahead, which is different from another technique called ahead-of-time compilation. Ahead-of-time compilation is like what we do in C++. You compile it, you have the end result, and then you can move it somewhere else to run it. But just-in-time will be, you have the source code, we compile it, and then we run it directly at the same way it, as long as it's compiled in parallel time, we can just run it. But V8 is a bit complex. There is a lot of misunderstanding about V8, and not because people misunderstand V8, not because people are misunderstanding it, but because V8 employs a lot of technique in order to make V8 run faster. In fact, V8 is the fastest JavaScript engine we currently have. And you will often see that V8 compiled JavaScript code into machine code without producing bytecode. In real world, that's not really true. That's why you will see in some documentation that V8 is an interpreter or a virtual machine. But I will mostly use the word that most people use, that V8 is a compiler. And then we will try to know why some people consider it as an interpreter or virtual machine. But because sometimes even me as myself, I consider V8 as a virtual machine. And V8 powers Google Chrome, NodeJS, as you all know, and also the Opera browser. It can run standalone or can be embedded into any C++ program. And furthermore, you can even embed inside another kind of program, whether it is Python, or as long as you can compile into C++ and have a binding to your language. Alternatives to this kind of program are Chakra, which is the JavaScript engine for Internet Explorer. Many people have bad feelings about IE, but I can tell you that Chakra is really fast. In Firefox, you have their own version, which is called SpiderMonkey. And I believe if you go into the source code, there are a lot of components related to monkeys. And then we have in Firefox an old implementation, which is called Rhino. And I believe if you look into Java, the Java programming language until Java 1.6, you will find the implementation of JavaScript that used to run in Java is based on Rhino. They embedded basically Rhino inside Java to be able to consume JavaScript. And then you have in Safari, Mac users, you have JavaScript core. So we choose V8 because V8 is the fastest one currently. Nothing else. You may have some preferences, but most of these JavaScript engine, apart from Rhino, are written in C, C++. Rhino was built in JavaScript, which is really easier to understand. But Rhino is really slow in terms of running at full speed. Rhino was much more built for educational purposes rather than runtime environment purposes. So alternative implementation of most JavaScript engine, in old JavaScript engine, we used to have this kind of implementation. So this is the kind of implementation you will find in Rhino, an old implementation of JavaScript. At that time, all JavaScript was considered as virtual machine because they end up having all the steps we previously had, as I showed you inside the compiler. At this level, you have the source code. This source code is fed into a parser and a syntax analyzer and a parser, which we just summarize it as a parser. You have an end result as an abstract syntax tree, and you have the execution engine that directly executes it. And when you have an execution engine like this is much more like a virtual machine because you have the stack call of the virtual machine, you have the heap of the virtual machine which will be holding a JavaScript object, and you have a garbage collector for memory management. So this is more like a virtual machine based. So you have the memory runtime data access area, and then you have the garbage collector. And most of the time, you also have a host external libraries. Like this is where the browser API comes in. And if you want to embed inside another application like NodeJS, if we were to build NodeJS inside Rhino, this is where NodeJS will come in handy. This is where Node will be plugged in. At this interface, you will see FFI. In the description note, you will see what these acronyms are all about. Abstract IAST is abstract syntax tree. FFI is foreign function interface. So this is like what the browser API is all about. JavaScript as a language will not know what document.getElement is all about. It is the browser that will provide those functions and set time in a set time interval, set time out. The browser will give those functions, and those functions are given through this component here called foreign function interface. But just as I can say, this is an old fashion of implementing it. So let's say the new way V8 and currently most JavaScript engine implements. As in the particular case of V8, V8 has a pipeline called, the V8 compiler pipeline has basically two compilers. First, a full compiler that generates good but not so great JavaScript, not so great machine code for any JavaScript language. It generates, the advantages of this full compiler is it's really fast. It generates code on the fly really fast. It does not apply any type analysis. So any errors that comes in, it just generates. If it cannot generate, it just throws it away and say, okay, I cannot work with this. And it uses what is called inline caching strategy at it runs. So the inline caches means whenever it compiles a chunk of code, it will just put it somewhere like a function. It will just put it inside a dictionary where the code is. So next time you find that function call, instead of recompiling again, it just fetches from the cache and then execute it. And then you have the second compiler, which is an optimizing compiler. The optimizing compiler produces a great code for most JavaScript, but it is slow. It recompiles hot function. What are usually hot function? Whenever V8 detects that, okay, this function like add is being called twice, 3 times, or more times, this function becomes candidate for hot function. Hot function means function that are mostly used inside your programming, your application. So whenever this function is declared as hot function, it gets a priority inside the cache area, and we cache it inside the inline cache, and then whenever we need that function, we call it straight away. So most of the time, as soon as from the inline cache, which is not a compiled code, when a function is detected as hot function, that hot function is recompiled by the optimizer, the optimizing compiler. And when it is compiled by the optimizing compiler, it's run faster than what is the raw compiled code inside the inline cache. So, and type are usually obtained from the inline cache. Type information and function information like classes, you already know that function in JavaScript are first class objects. So these are the types information, which is usually referred to as RTTI, which is runtime type information. Runtime type information are usually fetched from the inline cache. And some language features currently, such as try cache, are not implemented inside the optimizing compiler. That's something you need to be aware of. So don't expect, like, if you write try cache, that will be optimized by the compiler. But I think the teams will be trying to ship whatever optimization they have. But it has been said that there is a workaround with it, but I haven't had the time to actually look at how to have a workaround with it and just tell you guys. But I think that could be a research that all of you guys can make and find how idea about it. So you always, a V8 also support on top of that de-optimization. The thing about optimizing is memory is not something infinite. It's always finite resources. So we can optimize that the way we want, but sometimes there are some function that becomes hot function, but at some portion of the execution, they are no longer hot function. Like, let's say you enter inside a function call, a recursive function call, then inside a recursive function call, you will be calling factorial multiple times. That becomes a hot function, but whenever you are out of the scope of that function call, factorial is no more a recursive function, a hot function. So instead of keeping it there, we can just de-optimize it and then throw it away and then fall back to the full compiler, which is the normal one. In fact, there are other components that are underneath that we'll have a look at this picture. So this is like the V8 architecture we can come up with. So V8 started having just the full, which is in yellow, the baseline compiler. the second column, and the optimizing compiler. But then the guys realized that, hey, there is something going on here. Having a full compiler and an optimizing compiler is great, but this kind of like resource consuming, because some of the device we have nowadays, like mobiles, are not really a good candidate for the kind of computation we do with a fully fledged compiler or an optimizing compiler. So what the team decided was, okay, we are going to have an optional virtual machine which is called Ignition, and that is the part that is the first column, which is Ignition, and that the arrow pointing to bytecode. So basically Ignition was introduced later into V8. Also, at the optimizing compiler level, you see that basically V8 not only has two compilers, but it also embeds inside two distinct optimizing compilers. The first one that was in V8 was called Crankshaft, which is at the top on the third column. And the second one lately introduced, which is a better version, is called Turbofan. They all do the same job, and currently, as in Node.js or Chrome, Turbofan is the preferred one that is running. In older V8, you will see Crankshaft. So coming back to Ignition can be enabled in Chrome, Google Chrome, or turned off when you are compiling the source code of Google Chrome. So basically what Ignition does, mostly it is for mobile browsers, like the browser, the Google Chrome available on Android, and it helps consume less memory. And this is like a virtual machine. So if you call back, we recall at compilers, V8 generates JS into machine code without producing bytecode. That's why I was saying this is something to take just as an information, but in reality, V8 currently embeds a virtual machine, because Ignition is a real virtual machine that will compile into bytecode, and the bytecode is actually interpreted. And whenever we have an interpretation of virtual bytecode, you have this part of the picture, this part of the picture that's embedded inside, which is the virtual machine part. So that's what I can sometimes some people will call V8 as a virtual machine, because there is an interpreter inside. So basically this is the bigger picture, and most of the time if we stick into the baseline compiler will just generate only unoptimized code. Whenever the system detects that, okay, this is a host function, that host function is sent to Turbofan, or whether it is Crankshaft available, it is optimized. This optimized code is usually run, and whenever we detect that, hey, this is not needed anymore, we switch back to the unoptimized code, and thus the runtime just keep on fetching and running JavaScript. So if we come in the internal of V8 as a JavaScript compiler, how does V8 makes it happen? How does V8 makes things run faster? Compiling inside a language which is statically typed is really easy, because beforehand you know what an integer is, and you know that when something is declared as an integer, it never changes. But that's not the case for JavaScript. JavaScript is not a statically typed language, it's a dynamically typed language. So basically, when I say, okay, this variable a is an integer, that may change later on. That makes it really, really difficult for this kind of language to run faster. That's why compiled language like C++ are faster than dynamically typed language, because the runtime doesn't need to keep track of what is the type of this one, what is the memory layout of this one, because we already know that this is an integer, it is 32-bit, so the memory layout is always going to be 32-bit. If it is a long or a 64-bit integer, we already know that it's going to be 64-bit no matter what. and the compiler has already done the type checking, so you cannot put integer 64-bit inside 32-bit. The compiler will whether warn you or even forbid it straight away. But that's not the real world in JavaScript. So how does that happen? JavaScript will implement, V8 implement what is called hidden classes to operate. So in order to make it faster, it kind of mimic type information. It creates its own type information called hidden classes. Type information are really necessary for optimizing code. Type information is really valuable while you are generating the code, the code. You are optimizing and generating the code. You are trying to actually reshape the form. You need to know the abstract syntax tree. You really need to know what this abstract syntax tree is all about. If I cannot decide, okay, this is an integer multiplication, I won't really be able to apply the optimization rule we previously had in the other slide. So by creating that, by using this technique, V8 create hidden classes for object during runtime. An object with the same hidden classes can use the same optimized code. So how that work with the hidden classes? Let's say you have a function called point, which is basically will end up being a class, and then you pass in x, y as parameter. You have this.x and so on. We all know a constructor. Then you construct a p, a point which is p, by passing 11 and 22. Then you construct another one, which is 32 and 44. So you will end up having, on this blue, you will end up having this hidden class, which the layout will be, okay, the property which is x and y. The first offset in this layout will be 0, which is x, then the second offset, which is y. But then, whenever you create the first object, which is p, this object is generated from this optimized code from point, which is a hidden class, and the second one, q, is also generated from this one. So from this hidden class, we are able to run whatever you want to run for objects p and object q. So let's say we have now this kind of function and this kind of source code we are dealing with. And this function is just like the previous one. We also construct new point. We also construct here new point. So whenever we construct, we call for the first time new point by passing 11 and 22. Then we end up having, this is the first time we are calling the function point. And whenever this is the first time, we first create a hidden class, which is at revision, I can call this at revision 0. Revision 0 of the hidden class. And revision 0 of the hidden class does not contain anything. But then when you go inside the function, because this was the first time we called the function, point 1, the revision 1 is created by doing this.x equal x. And this is revision 1. Then whenever we do this y does equal y, we have revision 2. And this is revision 2 of this hidden class that we have here. From revision 2, we were able to generate p. Then we also go to generate q equal new point. And as you can see, the layout doesn't change, so we also generate q based on layout 2, based on revision 2, which is point 2 over here. But what happened with this third parameter, this third instruction here? We say, okay, q equals z, q.z equal 55. And whenever you do something like this, V8 will automatically detect, hey, this object q is not longer a valid candidate running inside this hidden function, which has version 2 of point. We also need to create another revision, another copy of the hidden class, but then while adding the third property, which is z. So whenever we do like this, that means first of all we are creating another hidden class, which is memory consuming. While creating the hidden class, we are adding an overhead of our program execution. So the bottom line here is like initialize all members inside the construction function. So even though like we are not planning to use a 3-dimensional point, it is always better if you could do this initialization this.z equal 0 or null whatever inside this point. If you do like this, then this third one will not be created. This one will just be replaced. The point 2 will just be replaced by this single version of the hidden class. And all of these objects will just point to this single version of the hidden class. So you have one single optimized code that will be able to run your program, which will make it run faster. I know that every time it's not easy to take care of all of this inside JavaScript, but basically if you want to gain some performance, this is basically what you need to do. And also, initial member in the same order. Like if I do X, Y, Z and come back and say, okay, I'm going to initialize it using Y, X, Z, then it's always going to generate another version of the hidden class. So also you need to avoid changes in the hidden class after the constructor is being called, just like we had these changes here. So basically for hidden class, this is how it basically ends up doing. We also have how V8 represent object inside its memory. V8 will use what is called tagging. Tagging, we will have the object pointer. Object will be represented by what is called a reference, and on a 31-bit size, the reference will be slotted, and on the 32nd bit, you will have a flag which is 1 for object, and you will have another flag which is 0 if it is we are dealing with small integers. If we are dealing with any other type, like double, float, or large integers, we will use what is called a larger object and use what is called boxing and unboxing. In many programming languages, we use boxing. Boxing and unboxing is like a type conversion. And let me tell you that this is really an expensive process, so you really want to avoid it. It's better to declare a variable as large as possible so that it is already initialized as a boxed variable, rather than initializing a variable as a small object and then later on boxing it as a larger one, or later on unboxing it as a smaller one. So boxing and unboxing is really, really expensive. This is something compilers really want to avoid in programming languages like JavaScript, C# and Java. Apart from the memory layout, you also have V8 use two ways of representing arrays. You have fast element arrays. These are the kind of arrays we usually deal with. And this is chosen by V8 engine. It's really, really fast, but it's only V8 will choose this kind of array for you if you stick with having an array where the indexes are integers. Like I create an array where the indexes are integers. But as soon as you start using an array with indexes of string or object, then V8 will switch to dictionary element. And dictionary elements are hash table, they are fast. But the way V8 will store it, fast element arrays are always faster than dictionaries inside V8. So you want your arrays as much as you can to stay as fast element, and that is using integer index as their key. Also, there is another performance gain which is monomorphic uses of a function. Let's say you declare a function which accepts x and y. Whenever you call this function xy point with integers, it's gonna create an optimized version. And as long as you call it with integers, you are going to stick with that optimized version. But as soon as you call function point with floating points, then you are creating another version, because V8 will need to compile, hey, we need to create another version of this function that accepts integer rather than integer that accept floating point or double. So that is called polymorphic calling a function with polymorphic usage. And because JavaScript is a dynamic language, it will not enforce you to always use function point using integers. So you are able to call function point with any type of parameter you want, string, floating point, but whenever you do that, you also lose some performance gains. So as we come over here, before going into how we can embed V8 inside our programming language, I would like to ask anyone if you guys have a question up till now about V8 or whatever we have covered so far. All right, it seems like you don't have. Okay, I guess some of, like Jasper, some are complaining that we are dropping off and on. I'm really sorry about it. But if we want to summarize, we were talking about optimizing the internal of V8 and optimization about V8 and how V8 lay out things in memory. So now I will be giving a demo, and I will also warn because at this demo level, because I was not really able to make compilation of V8 work on my version of C++ compiler, so I had to use a previously built version which was available on an old version of Visual Studio. So I'm just going to pop this in. I hope you guys can see my virtual machine. I think the full screen will not, yeah, I was really. Okay, so okay. Yes, we have it. So it's gonna be a bit choppy, but I guess I'm just going to compile once, run it and see. Then we are going to see to go about the explanation once. Can you guys see my screen, please? Because it seems dark on. Okay, so basically people can see my screen, my virtual machine. So what I'm trying to do here inside this application is embedding V8 inside a simple C++ application. And what I do, I just read a JavaScript file called main.js, which is available. Here, I just say print begin script, print this kind of argument, print this one also, var x plus and print x. So print does not exist in JavaScript, so it does not exist in V8, so we are going to create it. So basically, what I will just do, yes?
I think they cannot see the screen. They are seeing the same that I'm seeing here.
No, you are not seeing my screen. Sorry about the disruption. So I'm going to say, okay, let me execute without debugging. Yeah. So I hope you guys can see my screen. But basically what this script does, it goes read my JavaScript and then executed print. Then we have print in the console. We have print, which is 1, 3, 5, and 7. And also we do the calculation 123 plus 27 equal 150. We print the result of x. And then I just have my end program. This is a bit really slow, so I'm going to go somewhere else to go through the source code. Yeah. All right. Sorry, guys. I'm trying to see where I put my folder. All right. So we are back. I will just close this and then now go through V8 demo. Obviously, I will not be able to run this V8 because I don't have any C++ extension, and even if I had it, I cannot really link to all the libraries. So basically, this is, and I will send out the Visual Studio project for those people who want to try out. So basically, this is what we do, and this is a C++ code. V8 always, in order to embed V8, we use what is called object template and function templates. This is the base component for embedding V8. This is my small utility to be able to read any JavaScript file that I write. And these are like import. I'm sure some of the guys are familiar with C++, so this is really important to import here V8 as a library. Then I will first go inside my main execution. Inside my main execution, I will read through the main.js file and I will create a script name. Basically, V8 need any script you want to embed inside V8, you want to run inside V8, you need to give it a specific name, a name that is unique. And then once you have the name of the script, you also need to convert the JavaScript you had inside an actual V8 script that we call string, which is handle. V8 has its own string representation, so we will be transforming the script we just got from main.js, we transform that into V8 enable string. Then, just as I was saying, each script name must be unique. But because of this demo, I just use this one as the single name. And we create also the name of the string using this by converting this string we have here, which is a character pointer, by V8 enable string. And this is, as I was saying, the main component. The main component, the global object. In other environment, this is like the window. In the browser, this will be the window. So the global object is a new object template from V8. Whenever I construct the global object, then this is where I start to create my global variable, my global function. Like if you go inside the browser, you say, hey, window.set time out. So this is how these kind of function available in JavaScript are created. Inside the global object, I will set, okay, I want to set a new function which is plus, and then by passing the callback of plus. The new callback is a function template. Just as I said, we use object template and function template. The new callback that whenever the keyword plus is a function will be called, I want to call this C++ function, which is plus. And the plus, don't worry about it. It is defined somewhere up. Also, I want to define print inside my global environment, so I also need to give it print as a function template. The function template callback is also defined up, and then we need to create V8 context. V8 is really, really good at this because it is important to know that V8 can run multiple JavaScript at the same time. In parallel, you can run many JavaScript instances in the same time. And that's why the restriction of having, for every script, you need to have a unique name for it. Because it will cache it and you can run it in parallel. So basically what we do after the context is constructed, we just execute our string by passing the source code we constructed from here and the unique name of the string. So execute string. What does execute string will do? As you can see here at the top, we have created the global object, the handles, the scope, and the context, which are initialized inside our main function. So this is the print I was referring to. Let us go first for the plus. Then this is the plus callback. Whenever the plus is called in JavaScript, this function will be called back and it should return a handle with a value. Then all the parameters that are given from JavaScript perspective will be passing at this v8 argument. This v8 argument is like an array. Then with this array, we convert it to an integer 32 value. We convert the second one as integer 32 value. Then we return the addition of a plus b, the conversion, as an integer 32 value with the handle. So that's basically what we do. So we convert this inside C++ and we give it back to JavaScript runtime. And then we have the print. The print also comes with arguments. So if it is the first time, we make sure that we don't put any space. But for the following argument like 2, 3, or 1, we need to print space after the first one. So that's why this little one. So we look through all the argument. We just convert the print into ASCII representation. And this is a C call of printf. By using a template, we just output everything from our string that was given. And at the end, we do a print, end of line print. Because we are returning nothing, then we just return undefined. This is the same thing as just returning void. We do this because in C++, this is a requirement. Whenever you write, okay, I'm returning something, you need to return something. If you don't, it's not gonna compile. Then we have execute string. Execute string, this is the main component that takes the string and the name. It will construct context scope by using the context we are having, and we have a try catch because something bad can happen inside our execution environment. We don't want to crash out our C++ because somebody wrote a bad JavaScript. So we create a try catch which will help us catch some errors, and then we construct the script by passing the script and the name inside v8 script.compile. And this is where the magic happens. This will compile into our optimized code. We just store the result of whatever operation we have. If the compilation fails, we will have script.isEmpty. And in that case, we just return by outputting the error. Otherwise, if there is no error, we continue by actually running the actual script that we just compiled. And we save the result inside a value which is also handled v8 value. If the value is empty, then again we output the error that we could not have a value. But if the value is not empty and it is not undefined, we actually print the value. And that's what makes it. We compile our JavaScript main.js, we run it through, and the end result, we output it inside a C++ application, which was the console that you saw earlier in my virtual machine. So basically, at the end of the day, this is what you end up with. You are able to put together, create your own functionality inside C++, bind them to V8, and whenever JavaScript is called, call those functions, you call them. And so basically at the end of the day, this is what NodeJS does. They create C++ function like accessing the file system, doing whatever HTTP response to do, IO writing synchronously input-output, and then bind those functions into JavaScript calls. So whenever you call the JavaScript counterpart, the callback in C++ is called. And because C++ is the fastest runtime environment actually currently available, then that makes it Node.js run really fast at the end of the day. So basically, in terms of demo, this is what you all have in terms of JavaScript. So I think I will be running a bit against the chrono. So let's say if you have any question, I'm always expecting as we go along. So that was the demo about V8. Then let's finish off this talk on the Node.js. As we all know, Node.js is the server side of JavaScript. It uses V8 as a primary JavaScript engine, but You have a Chakra implementation at this following URL, so you can have a look at it. But there are other implementation with SpiderMonkey, but these are just like fun for fun, so you should not use them in a production environment. Although the Chakra version is really pretty advanced. And then Node.js excel on the event model, but Node.js itself doesn't implement the event model. The event model built inside Node.js is from a separate project called libuv. So libuv is the C++ library that implements asynchronous input-output. Mainly, Node.js has two components. The first one is the event engine, which is really fast and asynchronous, libuv, and the JavaScript engine, which we just talked about, V8. There are other libraries, C++ libraries, like the zip libraries for zipping content or streams, zlib. We also have support for OpenSSL, and of course, HTTP parser. There are other ones. Inside Node.js internal, as you can see from the V8 perspective and V8 demo, JavaScript and C++ can be connected using object template and function template. And V8 Node.js operate in kind of modules. There are two kinds of module in Node.js. We have built-in modules which are in C++, and that's like the one available in libuv and the one available as OpenSSL HTTP parser. You also have an exposition of those modules as public APIs, which are JavaScript modules. In JavaScript modules, you have two kinds. Native modules, which are part of the Node.js core libraries, and external modules, which are modules that we as JavaScript developer and Node.js developer usually build. Something like if you want to use Grunt as part of your Node module application, if you want to use CachDB libraries, and so on. So these are external modules. So as an internal module in C++, this is like an example of an external internal C++ module. This I have stripped out a lot of source code here. So this is basically the same example we just used as embedding inside Node.js, inside V8, embedding a C++ code inside V8. As you can see in the bottom, at the bottom here, you have something called Node Module Context Aware Built-in. In C++, this is like a macro. This macro will help us output all this module inside the C++ environment of Node while we are compiling, and it will also make it available this V8. So inside Node.js, you are able to access V8 as the core engine, and you are even able to know some statistic of V8. So if you look into the documentation of Node.js, you will see that there is a module called V8 where you can get, okay, currently inside my Node.js, what is the current heap size I'm running with? What are the current environment variable I have? And what is, if I can increment the heap size in order to get more memory, and so on. You are able to do that. And this is inside this example of module where Node.js is able to do those kind of stuff. Then you also have native modules. Native modules are extracted and injected. Native modules are basically what we have inside the FS module, the crypto module, and so on. So these native modules are actually JavaScript code. But how are they built inside Node.js? They are extracted inside a tool available inside the Node.js source code at tools/js2c.py. This tool is like a converter from JavaScript to Node.js. It's not a compiler. It won't like convert any JavaScript into C++. What it just does is extract the JavaScript code inside the file and then inject inside a .h native node.native.h inside an array called natives. So what we are able to do with that inside Node.js is we have this C++ function called define JavaScript. Whenever you try to compile Node.js, it will run this define JavaScript function, and it will get from that header file, which have an array called native. At this particular line, it will go inside native, extract the script name, and because each script or each module have its distinct name, so you don't have to worry about naming collision. And we get the source code, we compile the source code, then we set that source code directly inside our node environment. Notice that it is not compiled yet because we don't want to compile if the FS module, if your application shows a crypto module like, we don't want to compile a module like crypto module. If you take an example like rimraf just use a node module which just use FS module. We don't want to compile, waste time compiling the crypto module, whereas a module that an execution environment we are running JavaScript with doesn't need to run crypto module. So we don't waste time. We don't compile it first. We wait until this module is required. So whenever the module is required, this is where we compile it. So basically, the third one is called external module, and the way to support external module loading, the C++ module loader is exported as an object template and will be available as natives. Just the same way as V8 is available as process.binding, you will have native as the module. So I think this source code was really long, so I did not want to embed it here, but you will always find the link as a gist. So this is actually the node module loader example, the node module example, just as raw it is. It is pure JavaScript, and the function is just called node module, taking an ID. The ID is just the module we want to load, and the file name inside it will be the ID plus .js. So we are expecting a JavaScript file to be available. You have the ID, the .export, and this is actually how you have module.export available inside Node. You have a flag called loaded if the module has been loaded. Then the source file we have is protest.binding, native, just the native I was talking about. And you have a cache, because we want to have a cache to see is this module has been loaded or not. Then inside node module, this is your require function. Anytime you use this, say, okay, require.this function, this is what it will be called. First, we just check if it is a native module already available, that which means the current native module we are requiring, we just return the current native module. But if it is not, then we try to see if it is available in the cache. If it is, then we return cache.module export. Notice that how we don't return the actual module source code or run any. We just return the module.export. And that's why whenever you create a node module, it is only from the external world, what is available is module.export. Whatever you expose as module.export, this is what you will get. If you don't export anything, you won't get anything. Then if it is not available in the cache, okay, we then first check if that module file exists. You will see that module exists. We'll check, first of all, if the source file was already loaded. If the source file is not loaded, then we'll raise that, okay, the module does not exist. If it exists, then we create a node module giving the name, and then we push that inside the already module loaded. Then we create a new instance of the native module, and by passing the module, like let's say we are having our own module called Ivan, then we pass it by new module.Ivan. And because this module is loaded, we cache the source code we have just loaded, and then we compile it. Once we compile it, we return the module.export, because when we compile, we actually running it. So we return the module.export. So how does it compile? The compilation is somewhere down here. When you compile, we get the source of this module. We already know that this module source is available because it has been loaded. Then we get the source, then we wrap it inside a function. And the module.wrap is something here. So what it just does is return wrapper 0 with the current script we pass in plus native module wrapper.1. And module.wrapper is an array. The first part is this, and the first part is this. If you remember, this is actually what I was doing inside the ultra tiny compiler, wrapping the user source code inside an embedded function. So this will keep your module as private as possible because it is inside a single function, an enclosed function, anonymous function. And you will get inside your module export. This is how you get export. This is how you are able to require, because the required function will be passed as a parameter. The current module will be passed as a parameter inside. So your current script will be living inside here. You have access as a function parameter export, require module dash dash file name dash dash dir name. And so these are not like magic. This is the way these things happen to be inside your Node.js source code. So whenever we wrap this source code, then we have a final source code that we will compile. This runtime is run inside this context is from this native. It is a JavaScript function that is available from native. So we compile it, and we end up having the end result function that we call. So we call that end result function by saying this.export, this.native.require. So the require module, the require function we just had it, we pass in as a require function, and the current module will be this, and the file name, and so on. So we end up executing your function by passing these parameters, so you can access it inside your function, your module, which is being embedded as a private. And of course, we flag this module as loaded so that we don't reload it again later on. So basically, at the end of the day, this is how your Node.js application will be embedded inside a source code file. I hope from this source code you get really the idea how Node.js basically does the magic at the end. I could not get the time frame was really short to talk about libuv, but libuv is really an important part that we cannot forget about Node.js, because that's even the core of Node.js. V8 is important, but Node.js is what libuv is what makes Node.js today, because everyone uses Node.js because the way the I/O implementation is done, it's really fast, and this is because of libuv. So I really expect you guys, for those who want to go deeper, to look inside libuv. So I will just stop here and say really thank you guys for attending and listening to me. I hope it was not boring. I hope it was entertaining. So if any of you has a question, I'm really open.
Thanks, Anas. No questions. I just wanted to say that was really, really interesting. I think that was a fantastic talk. It was a really good amount of tech and depth, I think, then, so that everyone can follow along. Yeah, I really enjoyed it.
Yeah, he said. Do we have questions? Yes, I'm open to questions.
Actually, one question now that I think about it. I mean, it's kind of just been a given. You've said throughout the whole talk that V8 has been the fastest JavaScript engine without question, but that surely can't be the case in all contexts. Otherwise, there would be no point in other people using anything else. Are there statistics on comparing V8 to SpiderMonkey and Chakra then?
Yes, I found some comparison statistic. I think that's a good point that I should have included, but as the benchmark currently shows, V8 is definitely the fastest running JavaScript engine. It's not like it's ahead of the others by a large margin. It's not ahead of the others by a large margin because Chakra, which was introduced in Internet Explorer 10, is really, really fast also. It employs some kind of good techniques, So it's not something that is an absolute statement that always V8 will stay the leading one. But as it stands currently, some of the statistics shows that V8 is definitely the one that is ahead, even if it's not like by a quite large margin. But also, these compilers are being always taught and improved again and again. They try to tweak in some areas, so it's kind of really difficult to have a benchmark every day on top of them, but usually these kind of benchmark are usually run twice or three times a year. So the latest information I could get is that V8 is the fastest running.
Oh. I mean, you would think that there are some advantages and disadvantages between them as well then. It might be that, Chakra runs like some particular code a little faster, I assume. It'd be strange to see that it runs like absolutely everything slower.
Yeah, definitely. And talking about the speed as well. We are only talking about the JS engine and the techniques, because most compilers depends on how the optimization technique is done. So when I take a source code, for instance, called X, I run it to inside one JavaScript engine or one compiler, they might not end up optimizing the same way. So you might end up having some part of the source code which is better compiled in better optimized in one compiler than the other. So at the end of the day, it also depends on the source code you are actually giving to the JavaScript engine. So let's say I'm doing a benchmark, I'm giving already neat source code to the compiler. Of course, it's going to generate really clean code. But if I'm giving really hard source code to the compiler, sometimes the compiler will just generate code that is not optimized and just stop away. So this is like not really an absolute statement, but usually people try to have a comparison and give a better idea. But definitely, at the time Node.js was created, Chakra was not available. Chakra is also really fast in Internet Explorer, but Chakra was not available. And SpiderMonkey also was not really actively used inside Firefox. Firefox was using something else which I really don't remember. They actually rewrote JavaScript engine in Firefox inside SpiderMonkey, and SpiderMonkey also came later. So I think these are all the decisions that made the Node.js teams use just JavaScript as an engine.
V8, you mean?
Yes, V8, I mean. But there is also this kind of thing that say, well, C++ is complicated to work with because you need to do memory management yourself. So let's say I'm given today a project to work with, and I feel like, well, this project optimization running really fast at fast pace is not a big issue. I could choose Rhino, which is an old implementation but really works well, and it is Java based, so garbage collected. I don't need to worry about complication about memory. Any other question? And I hope.
Did you manage to record everything as well then?
Yes, I think so, but I cannot say yes until I press I press the button stop record and see that everything was recorded.
Okay, cool. Let us know. Hopefully, that'd be fantastic if we could host it somewhere and everyone has access to it afterwards.
Okay. And also the C++ source code and the project file will be handed over to you over the weekend, so you can know what to do with it.
Cool.
Okay.
Okay. It sounds like we should probably wrap up there then.
Okay. Thank you, guys.
Thank you, guys.
Thanks very much for the talk, Evans. That was fantastic. It was good to see the Liberia crew representing.
Thank you.
Thanks. I'm not sure who the next talk will come from. Looking for nominations if anyone wants to volunteer for the next tech talk in a month's time or so.